of students with the same birthday. Okay, and then usually what people will do, their first reaction is to say E of n. You just plug in the formula as the sum I equals 0 to, I guess, however many students there are, n, of I times the probability that n equals I. Right? If you do this, it turns out that it's going to be a big messy formula. There is a way to collapse it, but it's not easy to see. Much easier way to do the problem is to be smart how you choose your random variables. Okay, so the hint is you're going to define another random variable. I of ij. Okay, it's an indicator. It's going to equal 1 or 0. 1 if student number I and student number j have same birthday, and 0 otherwise. Okay, and that's the extent of the hint I'm going to give now. Okay, but think about it. Think about how I relates, these i's relate to the n, and what you can say about the expected value of n in the context of these i's. And if you do that right, it'll be easy to solve. Okay. Any questions? And another piece of advice about the homework that I give in this class. It's hard, even though there's only 6 questions. I mean, the first 2 homeworks aren't going to be that bad, but you really don't want to wait until the last night to try and start them. You'll never learn anything that way. These require thought, and I mean, if you're knocking them off one at a time, you know, I don't know, you're a genius, or you shouldn't be in this class because you already know everything. So they're meant to be hard. They're meant to be challenging. So don't start them at the last minute. You're not going to learn that way. And again, the homework is not a big part of your grade. And you can easily copy off the person next to you, or your friend, or whatever who's taking the class. You'll get full credit on the homework, but if it's not going to help you, that method is not going to help you on the midterm and final. And like I said, I don't count, the homework is 20% of your grade, but everybody gets about the same grade on the homework. Everyone gets within the ballpark of like 80 to 100%. So when I do the computing the grades, it's on a relative scale, right? So unless everybody aces the midterm and the final, not everyone's going to get an A. So you come to me and say, I screwed up the midterm and final, but I was doing, I was acing the homework. If we never interacted, I'll say, congratulations, and I don't know, maybe there's some sort of reward for that. But you get my point, right? Okay. So no questions. All right. So take a look at the homework. No office hours today, because I have this visitor. So you can schedule an appointment if you want to meet with me this week. All right, send me an email. Okay. Okay, so last time we were going through discrete event probability, and that's where we're going to continue. So any questions about where we left off last time? Do people even remember where we left off last time? What can we say about e of x plus y? Anybody? Sorry. With e of x plus e of y. And when is that the case? Always, yeah, okay. Okay, and independent or not? Okay, so remember that. Okay, something else I want to talk about is independent samples. So for instance, toss a coin multiple times. Or roll a die. Or choose socks from a drawer. Yeah, from a drawer. With replacement. Okay, by with replacement, what I mean is you put the socks back you chose. Right, so you can, right, there's two ways you can look for a pair of socks. You can pick out a pair of socks. If it's not the one you're looking for, you put it on the side, you keep picking. That's not with replacement. With replacement means you pick a pair of socks, it's not the one you want, you put it back, and you reach in again, you pick another pair of socks, it's not what you want, you put it back, etc. Okay? So what does it mean to say if the samples are independent? Okay, so let's see. Let's do this carefully. So what I'm going to do, if the samples are independent, it means, so let x sub I be a random variable that describes something about the ith time the event is performed. Okay, so for instance, flip a coin n times, x sub I can equal 1 if I flip his heads, 0 if tails. Okay. Then the samples are independent. Independent if for all values of x and for all values of y. So let's say let's say ith and jth samples. Ith and jth samples are independent if for all x and for all y, probability that x sub I equals x and y sub I equals y equals probability that x sub I equals x times the probability that x sub I equals y. Okay, so we say samples are independent if you can define this particular random variable. Okay, where the, sorry, what am I doing? X sub j, x sub j. Okay, you have this random variable where the random variable describes the ith toss or the ith event, right? And the probability that the ith event has a certain outcome and the jth event has a certain outcome is the probability the ith event has a certain outcome times the probability that the jth event has a certain outcome. That's what independent sampling means, right? So we're just going to say a lot of the time, we're going to flip a coin, and the flips are independent from one another. This is what we mean. Okay, and it's what you've used in your probability class time and time again. Right? If I say, so if I say a coin is flipped, each flip turns up heads with probability P, and the flips are independent, okay, this is a shorthand notation. Really, you're talking about the distribution that describes the flips are independent from one another. Okay, what that means is, for instance, the probability to get 3 heads is going to be P cubed, right? P times P times P. So let me say this more formally. Let's do the whole thing formally for a second. Sort of a quick review of what we went over in the first class. So omega will be the space of flip a coin. That's independent tosses. Probability P of being heads. An infinite number of times. Okay, so that's our event space. I'm going to flip this coin over and over and over again, millions of times. Let's define some random variables now. So omega, little omega, in omega, is a series, an infinite series of coin flips. Right, so for instance, omega could be heads, tails, tails, heads, tails, 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 heads, 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 going on forever. Okay, let's see. So let's call it n be the number of heads the first 3 coin tosses. Right? And also let SI equal 1 if I tosses head. Zero otherwise. Okay? So all we're saying is, what are we saying? Yeah. Probability that n equals 3, okay, is the probability that x1 equals 1, x2 equals 1, x3 equals 1, right? And because it's an independent tosses, we use that independence relation, and this just equals the probability that x1 equals 1 times the probability that x2 equals 1 times the probability that x3 equals 1, which is p times p times p, which is p cubed. Right? Everybody with me? When people think about probability, they just start here. Say, oh, it's independent with probability p, means I can multiply them together. Well, this is what it means more formally. Okay? And remember, also here I use the shorthand again. Remember, random variables are really functions, so this should be n of omega, xi of omega. Right? What else did I want to say? Yeah. Suppose we wanted to compute the probability that n is 2. Well, that's going to be the probability that x1 equals 1, x2 equals 1, x3 equals 0. So that's and then we also have the or x1 equals 0, x2 equals 1, x3 equals 1, or x1 equals 1, x2 equals 0, x3 equals 1. Right? Those are all the ways in which you could get the outcome happening twice. Which equals the probability that x1 equals 1, x2 equals 1, x3 equals 0, plus the probability that x1 equals 1, x2 equals, x1 equals 0, x2 equals 1, x3 equals 1, minus the probability that x1 equals 1, x2 equals 1, x3 equals 0, and x1 equals 0, x2 equals 1, x3 equals 1. Right? I mean, that's just applying the rule we talked about before with the Venn diagram. This is A and this is B. And this is A and B. Probability of A or B is probability of A plus probability of B minus the probability of A and B. Right? So I took care of this first OR, and now I've got to take care of the next OR. Sorry. Well, here we've extended this. We've extended it to 3. The way I did it, you got 3 samples. Right? So you got A, B, and C. This is A and C, C and B, A and B, A, B, and C. And the probability of A or B or C is probability of A plus probability of B plus probability of C minus probability of A and B minus probability of A and C minus probability of B and C plus the probability of A, B, and C. Right? Inclusion, exclusion. Everybody familiar with this? It's just the extension of this rule to when you have more cases. So I'm just writing that out now here. Which equals, plus. Well, so let me, plus, following the same order. x1 equals 1, x2 equals 0, x3 equals 1. Minus this, minus probability x1 equals 0, x2 equals 1, x3 equals 1. And x1 equals 1, x2 equals 0, x3 equals 1, minus the probability that x1 equals 1, x2 equals 1, x3 equals 0, and x1 equals 1, x2 equals 0, x2 equals 1. Right, I think those are the 3. This is A or B, A and B, A and C, B and C, or in some other order. And then again, plus the whole thing. x1 equals 1, x2 equals 1, x3 equals 0, x1 equals 1, x2 equals 0, 1, 1. x1 equals 1. Right? And all of these are just clearly 0 in this case. Why? Yeah, exactly. I mean, this one here says x1 equals 1 and whatever, and x1 equals 0. x1 can't be 1 and 0 at the same time. So this is clearly 0, and you can find a similar contradiction in each of those. Okay, so probability that n equals 2 is just going to be probability that x1 equals 1, x2 equals 1, x2 equals 0, plus the probability x1 equals 1, plus the probability x1 equals 1, x2 equals 0, x2 equals 1. So you could have just looked at this and said each of these are mutually exclusive, so we don't have to worry about the whole rest of it. And again, because these are independent coin tosses, right, this becomes probability x1 equals 1 times the probability x2 equals 1 times the probability x3 equals 0 plus the probability x1 equals 0, probability x2 equals 1, probability x3 equals 1 plus the probability x1 equals 1, probability x2 equals 0, probability x3 equals 1. Okay, which is p times 1 minus p plus 1 minus p times p plus p times 1 minus p times p, which is 3 p squared times 1 minus p. Okay, there's a much easier way to solve the problem, but you should always be able to go back and do it this way, because we're going to be faced with problems. Once we start doing harder and harder problems, you have to be able to have this intuition to follow it through in this form. And you also have to be able to and you don't always want to work it out like this, so you also have to know when you can sort of jump ahead. But probability gets confusing because people try to shortcut their understanding of this stuff. And they just start using the formulas without really understanding why they work. If you understand the background behind it, then it's always easy to sort of derive why things work, and then you never get confused anymore. So why did I do all this? Now I'm going to show you the shortcuts. Okay, well, so we were talking about independent sampling, which we're going to be using a lot. Okay, so now how do you do the shortcuts for these? Oh, and identical samples. Means that each sample drawn from same distribution. Coin toss, where each toss comes up heads with probability p. Okay, since that's true for each toss, implies identical distribution. Okay. Here's a pair of dice. Okay. Let's see. Here's the threes, and I've glued them together with a little rod there. Okay, so they both face the same way. When I roll this dice, it's always going to both die are going to come up the same value. Okay, so let's let x be the value of the die on the left, and y is going to be value of die on right. Okay, and they're glued together. Okay? X and Y are identically distributed. Right? Meaning the probability that x equals x equals the probability that y equals x for all x. Right? I mean, whatever the left die comes up, the right die is going to come up as well. If the probability the left die is going to be 2, it's the same as the probability the right die is going to be 2. Right? Because they're glued together. But they're certainly not independent. Right? The probability that x equals 3 and y equals 3 is going to equal the probability that x equals 3, which is not going to equal the probability that x equals 3 times the probability that y equals 3. It also equals the probability that y equals 3. Right? People with me? Who gets it? Who's still catatonic from waking up so early in the morning? Drink some coffee. Be better off. Oh, you got it. Finish and slam it. No. Huh? All right. Okay. Okay. Okay, something that's going to be important is what's called the choose function. Right, usually written like this. And choose k means it's the number of ways to choose k items from n when the order of choice is not important. So for instance, there's question. Yeah, the distributions would still be identical, assuming the dice have the same, they're built the same way, right? 1 out of 6 odds, yeah. I just wanted to give an example where they were identical but not independent. Okay. Yeah. Okay. So getting back to the choose function. Okay, the number way to choose k items from n when the order is not important. So if I say I'm going to pick 4 students in the class here out of 30 of you, and I'm failing you, no matter how you do in the class. Okay, whether you're the first one picked or the 4th one picked, you don't really care. That's what we mean by order is not important, right? So if I say, well, I'll say you don't care if you were picked 3rd or 4th, right? You're going to fail. You're equally screwed either way. So hence, order is not important, right? If I say I'm going to give an A, B, and a C, and a D to you, and you, then the order is important, right? Assuming you care about your grade in the class. Okay, so people have seen this before, right? People know it equals n factorial over k factorial and minus k factorial. Everyone knows what factorial is? Right? I factorial is I times I minus 1, I minus 2, 1. Down to 1. Okay? Can anyone explain to me why it equals this? Yeah, BJ.
They divide out the terms that you don't need. So the term on the left, the k, that makes sure that gets rid of the term on the right gets rid of, make sure that you only have the first 4 or the first k terms. decay gets rid of the order effects.
Yeah, right idea, but right idea, but you're not really getting rid. It's a little bit more intricate than that. So let me go through it. There are n factorial ways to order n items, right? And there are n times n minus 1 times n minus 2 times n minus k, I guess, plus 1 ways to choose k of n items where order is important. Right? So if I were to take the students in the class and I wanted to order you, meaning I was going to assign numbers to each of you, I could choose any n of you and make you number 1. And then there are n minus 1 of you left. So I could choose any n minus 1 of you and make you number 2. Choose any of the n minus 3 remaining and make you number 3. Right? Hence there are n times n minus 1 times n minus 2 times n minus 3 ... ways to choose n people and order them. Right? Everyone familiar with that, right? So if I stopped after only choosing k of you, there are this number of ways to choose you. Right? N ways to choose one person. N times n minus 1 ways to choose 2 people when the order matters. N of you could be number 1, and then once I've taken that person out and made them number 1, n minus 1 could be number 2. Right? Okay. So so far this is n factorial over n minus k factorial. Right? Now I've chosen k of you where the order is important. Right? K people where the order is important. Okay? How many groupings are going to contain the same k people? Huh? K factorial. Yeah. So consider a group of. I mean, maybe now it's easier to choose letters in the alphabet. Suppose I've chosen 5 letters out of 26. Okay, suppose I've chosen A, C, F, G, K. Okay? If the order was important, how many different ways could I have chosen these? How many different ways could I have chosen these 5 letters? There's k factorial ways, right? So you can take all the different groups of people. Or of letters, whatever. And say this is the group ways could have chosen A, B, C, D, E. And this is the ways I could have chosen A, B, C, D, F, etc. And if you look at all the ways, right, there are 5 factorial ways in which the same group of people could have been ordered. And since it's the same 5 or k factorial for each of them, you can then divide this quantity by k factorial. It's because regardless of which people I chose, or which letters or whatever, there's always k factorial groups that would have had the same set of people, just in a different order. So you can divide out by that quantity. Okay? You can take this quantity, you can bin them into groups of size k factorial where they all have the same sets of people. And there are no bins that contain the identical groups of people. Each bin has k factorial orderings of the same group of people. People with me? Okay, so you can divide by k factorial because each distinct group of unordered group of items chosen has k factorial possible orderings. So if I don't care about the ordering, because every possible group has the same size k factorial, I can divide out by that. All right? Okay. ID samples stands for independent and identically distributed. Okay, so we're keep flipping the same coin or the same die over and over again, so the outcome is equally likely each time, and we're not using any glue. So each flip is independent from the previous one. That's what we mean by IID. Independent, there's no commonality, and identically distributed. Okay. So if you have a coin toss, it's heads with probability P. And it's IID. The process of flipping the coin is independent and identically distributed. Okay. Suppose we do n coin flips. Okay. Let x be a random variable equal to the number of times the coin comes up heads. What's the probability that n equals k? Anyone? Yeah.
Choice k to p power k to 1 minus p whole power.
Why?
Always choose k places in n to interchange these k heads. And the grouping is not, the order is not important.
Okay. That kind of explains the interesting state. What about this one? Yeah.
Probability that it comes at k times is q to the k, and the probability of the alternate case is going to be a complement for all of it minus what you expect to happen. So it's all of what's left to the all of what's left to all of what's left, and the all of what's left in the probability to the power of all of what's left in the not even.
So, all right, you guys are on the right track, but. See, it's funny when you have the right answer, okay, and you kind of got the right intuition, it means you kind of understand it, but not really. All right, so I know we all have an intuition why this is true, but let's try and understand why it's really true. Okay, so we flip the coin n times. Let's do an example. Let's say n is 3, n is 5, k is 3. Okay, so omega, big omega is all possible ways you can flip a coin 5 times. Right? I can enumerate all of them. There are how many elements in the set? Huh? Somebody speak up. Bold. It's okay to be wrong. Yeah.
Is it 2 to the 5th?
2 to the 5th. Right? Each flip can be either heads or tails. It's like, write this out in binary. You got 5 bits. Numbers can go from 0 to 31, 32, 2 to the 5th. Right? 2 times 2 times 2 times 2 times 2. Could be heads or tails, could be heads or tails, could be heads or tails, could be heads or tails. And, think. All right. So that's omega. For which little omega and big omega does, what do we call it? X of omega equal 3. Right? You got to have 3 heads. So the answer is HHHTT, HHTHT, HTHTH, etc. Right? How many of these are there? Four. Give you a hint. There's 10. I'll give you another hint. I'm not that good at working them all out that fast. How did I know that?
Dice.
5, choose 3. I got 5. Let's see. How do I? Yeah. How many ways are there to choose 3 heads out of 5 coin tosses? I mean, so in some sense, I'm listing them here, so the order does matter. But the point is, I want 3 heads out of 5 tosses. I don't care what order those heads appear in those 5 tosses. Right? There's 5 choose 3 ways to do it. 5 choose 3 ways to write down 3 H's and 2 T's, where I don't care about the order of the H's and the T's. Okay? I'm taking a bit of a shortcut here. All the omegas have the same likelihood of occurring. What's the probability of omega occurring? What's the probability of one of these events happening? A particular event. Heads, 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 heads. Huh? 1 over 32. Okay. No, I'm wrong. Sorry. It's not true. They're not all the same. What's the probability of HHHHH? It's identical. It's an IID random variable. Sorry, it's an IID flipping process. Okay, where the probability of a heads coming up on any flip is p. So what's the probability of all heads? P to the 5th. What's the probability of HHT HT? Yeah. P to the 3rd, 1 minus p to the 2nd. right? Well, that's could put in one other step. It's P times 1 minus P times 1 minus P. First flip is heads, second flip is not heads, and the only other option is tails, so the probability of tails is 1 minus P, right? 1 minus the probability that's heads times P times 1 minus P. And since multiplication is commutative, distributive, whatever lets you write them in, rearrange the order. It's P cubed times 1 minus P squared, right? What about P of H, TT, HH? Same thing. What about P of omega when omega has 3 heads exactly? Same thing. P cubed 1 minus P squared. Right? And the probability that n equals, well, let's do 3, right, is the sum of omega where, what am I thinking? There are 3 heads tosses exactly P of omega, right? The samples in your sample space, only one of them can occur at any given time. So I'm saying, HHHTT occurs, or HHTHT occurs, or etc. So I can just add those P of omegas together, and I just want to add up the ones where there are 3 heads tosses exactly, right? That will give me the probability that n equals 3. N is the number of tosses. N is the random variable that describes the number of tosses that were heads when applied to one of the samples, right? Everyone with me? Yeah, Sebastian.
I'm a little confused by the X and the N. Is it the same?
Ready search? Yeah, that should have been n. We were I defined n. Oh, let x be the sorry. Yeah, x and n have been the same all along. So this should have been x, x, x. Okay, thanks. Okay? Well, what's this? We said we know that this value is always going to be P cubed times 1 minus P squared. Right? And how many terms are there in this sum? 5 choose 3, right? So that's how you get 5 choose 3 P cubed 1 minus P squared. Or if you want to generalize, right, there's the general form of the formula. For what's the probability that when you toss a coin n times, the coin is probability of being heads, probability P of being heads, that k of the times it comes up heads, right? The point is that of your possible outcomes, the probability of any given outcome is that, and there are n choose k outcomes. Sorry, the probability of any outcome that has k heads is going to be that, and there are n choose k outcomes that satisfy that property, that there are k heads. Okay? Okay, when is this true? Always. All right. When are you going to remember that? Always, all right. What about this? E of x times y. When is that true? Huh? Yeah. Definitely true when they're independent. Sometimes true even when not independent. But not always. Most unfortunate. I mean, so many times when you're solving problems, you wind up with, you're multiplying random variables, and if they're not independent, you just can't do that. That's the fact of life. But when they are independent, you can do it. Okay. Any questions? Okay. Conditional probability. Okay. Written like this. Probability that x equals I given y equals j. Okay. You say x equals I given or conditioned on y equals j. Okay? What's the, oh, let's just write down. This is defined. Definition. Defined this way. It's the probability that x equals I and y equals j divided by the probability that y equals j. Okay? Someone says conditional probability, it means this, without any intuition. Okay? But sometimes it'll be useful to use our intuition, although sometimes it'll screw us up. It's kind of like, well, maybe I'm dating myself here. Everybody's seen the movie Star Wars, right? The original one. Use the Force. Sometimes it's better to have the hood over your eyes. That's probability. You can think of me as your Obi-Wan Kenobi, right? And you are all Luke Skywalkers. Is there a less geeky example? What about this guy Shinobi, right? The new movie, the blind guy, guy with the sword who can, he's blind but he can kick everyone's ass, right? I bet he would know his definition of conditional probability. He would not get flustered. Is it Shinobi? Is that the right? Huh? Zatoichi. Yeah. Okay. Have you seen it? Has it come out yet? Oh, jeez. All right. I bet I saw Star Wars before you did, though. I saw that when it came out. You probably weren't born, right? You probably weren't born yet. Yeah. You guys, well, I was a bit, well, it's like the first, the amazing thing about the first movie is the special effects compared to all movies before it. It's just phenomenal. That ship going over in the beginning. Yeah, I guess, all right, never mind. See, it's a weird thing being a professor because over the years and years, you're really getting older. But it appears like the students are getting younger and younger. It's all relative. You'll see what I mean. So my dad always tells me, you're getting old because first the police start looking like kids, okay? Then the doctors start looking like kids. Then the judges start looking like kids. When the judges start looking like kids, you know you're old. you know you're ready to. But it's scary, man. You know, right? You're probably at a young enough age where if somebody tells you like move your car, you can just be like, if they're younger than you, you're like, buzz off. Like I got cops telling me to move my car, and I look at them, they're like, look like little kids. You say, yes, sir. That's the other thing my dad taught me. Never mess with cops. Cop tells you to do something, you do it. You don't question it. We were at the airport one time. Actually, it wasn't even a cop. It was, I guess, like a security guard there. And he was like, we pulled up to the side of the curb, and my mom got out just to, I don't know, drop off a package or pick up some tickets. Like she was literally running in and running out. And the guy comes over and he's like, move your car. And my dad was like, but, and the guy's like, I said, move your car. My dad was like, yes, sir. And I asked him, why didn't you shouldn't have moved. We were right. He's like, don't argue with cops. So, as you get older, it's, still gotta remind yourself that that's true, even when the cops start to look young. But I digress. Okay, back to conditional probability. So, what are we doing when we're talking about conditional probability? We're normalizing to what we know happened. Okay, so here's our space of possible events omega, right? And this mass, this space has probability 1 or size 1, right? If you chunk it up into the different omegas, right? Omega 1, omega 2, omega 3, omega 4, omega 5, right? They add up to 1, right? And for some of these omegas, it's going to be the case that y equals j. So let's say this set over here. Let's say for this set, our random variable y, describing these omegas, equals j. Right? All we're doing is we're normalizing. We're saying, forget about this part. Let's take this part where y of omega equals j. Let's make this 1. Make this size 1, and talk about the probability of things happening in this new space. Right? So this chunk is renormalized to be size 1. Right? So what am I talking about? The sum over omega, where y of omega equals j of p of omega divided by the probability that y equals j. These are the same thing, right? The probability that y equals j equals the sum over the omega where y equals j. Right? So this is going to be 1. I mean, that's the renormalization. Okay? And so you can imagine if we want to know what's the probability that x equals j given, x equals I, given y equals j, what we're doing by definition is the sum over omega of the omegas where y of omega equals j and x of omega equals I, p of omega over, probably y equals j. Right, so it's normalized. Just a bunch of ways to look at the same thing. Right, this is the probability that y equals j and x equals I. Right. Okay. X and y are independent random variables. Independent. How can I simplify that? What's that probability? P of x equals I, right? Yeah, Ari? P of x equals I. Huh?
What should be that?
P of x equals I. Right? Why? Somebody give me the intuitive reason. Somebody give me a formal proof. Yeah, Ron.
They're independent. Y has nothing to do with X.
Yeah. Right. If they're independent intuitively, y has nothing to do with x. So the probability that x equals I, given that y equals j, now who cares that y equals j? Doesn't tell me anything about x, right? They're independent. So it's just going to be the probability x equals I. What about the formal proof? Yeah.
That P of y equals j cancels out. When you multiply that, you multiply the and out, and then the bottom cancels out.
Yeah. By definition, this is the probability that x equals I and y equals j divided by the probability that y equals j. And what? How do I?
You can say P probability x equals I, probability y equals j.
Yep.
Multiply
Because of their independence. This equals probability that x equals I times probability that y equals j. Right? Okay. The intuitive method, the Obi-Wan Kenobi or Zatoichi. Zatoichi. Thank you. Method. All right. You must master both methods. Ah. Actually, maybe the Obi-Wan Kenobi method is really more the intuitive method, right? I mean, the Force, you've got the hood, but it's also like stretch out your feelings kind of thing. So that sounds more like intuitive. Anyway, all right. You get the idea. Did that. Okay, Bernoulli process. It's just a term for IID samples that can be yes or no. Yes or no, true, false, heads or tails. So you have this one event occurring with probability p. The possibility that event doesn't occur is probability 1 minus p. You keep flipping it over and over and over again. Okay? So we were doing Bernoulli processes before. And this is the distribution for the number of times that the item comes up true when you the probability that the item comes up true k times when you take n samples, and the process in which you're doing the sampling is a Bernoulli process. Okay? And let's see. trying to think of a good conditional probability problem. There's a good one on the homework, right? The sixth question. That's a conditional probability problem. Professor Rubinstein comes in and might say something. The TA might hear it, might not, might convey it. Maria might be there, might not be. What's the probability that Maria gets the message given that Professor Rubinstein? I don't remember the question, but something along those lines, right? But you'll see, to solve that problem, better to go by definitions than by trying to reason it out. It's, there's just too much going on there, even with just three people involved. So I'm trying to think of a good example like that. Okay, let's do this. Let's do toss a coin 3 times. So that's omega. Coin is IID with probability P. Or I could just say Bernoulli with probability P. Okay? Let n be a random variable equals the number of times heads comes up. And let's let t be a random variable equals 1 if second and third tosses are the same. Zero otherwise. So let's do probability that t equals 1 given n equals 2. Yeah, Patrick, right?
Are we to assume, when you said Bernoulli with probability P, that one event has the V or the other event?
Yeah, the probability that comes up heads will be P. Yeah, you should have to specify, but usually, I'll usually specify, like in a networking setting, packets are lost with probability P, packets make it through with probability P. You're sending multiple packets through a link, they're lost. The loss process is a Bernoulli process, or it can be just, the packets are lost with probability P, it's identical, it's independently distributed, etc. Okay. Yeah. So I should have said with heads, coming up with probability P. Okay, so what is this conditional probability? How would you solve this? It's not so easy intuitively, right? I mean, well, I know that it came up heads twice, but are the second and third flips the same? Like, well, if the second and third flips are both heads, and the first one was tails, or if the second and third were tails and the first one was heads, you could do it, but it's not just that probability. It's that probability conditioned on the fact that the n is 2. Okay, but you just apply the definition of conditional probability. Probability that t equals 1 and n equals 2 divided by the probability that n equals 2. So t is 1 and n is 2. So you got 2 heads, and the second and third tosses are the same. So how many ways can that happen? There's really only one way, right? Second and third tosses are both heads. First toss is tails. So the probability of this is just going to be, of the numerator, is 1 minus p times p squared, right? And there's only one way, only one order in which that outcome can happen. Here we do care about the order. It has to be tails, heads, heads, right? It has to be tails, heads, heads, because the second that satisfies second and third toss being the same, and there are exactly 2 heads. right? And what's the probability that the second and third toss are the same? What if P is 0? What if P is, it would be half if P equal to half. Yeah. Denominator is P squared plus 1 minus P squared. The last two tosses are both heads, or they're both tails. Whoever said, who said that? Sebastian. Okay. Sebastian kind of took a shortcut. He knew that the first toss didn't come into play. Okay, you only have to look at the second and third tosses because they're independent samples, so you can just sort of rule out the first one. So this is the probability that the second and third toss are both heads, and this is the probability the second and the third toss are both tails. It's only two ways that oh wait. N is 2. Sorry, I'm doing T. That's the probability that T is 1. Probably that N is 2. Probably that you get 2 heads. Ah, shit. Sleeping with the rest of them. Good thing class is almost over. No, really. There's like 20 erasers in there. All right. Well, so what's the probability that n equals 2? Huh? Yeah. It would be 3 choose 2 times p squared times 1 minus p. Right? Which is just 3p squared over 1 minus p. Right? So it equals 1 minus p times p squared over 3 choose 2 p squared times 1 minus p, which is just going to be 1/3. So given that heads comes up twice, what's the probability that the second and third tosses are the same? It's 1/3. Doesn't even matter what p is. Pretty neat, huh? I think if p is 0 or p is 1, you may have some trouble, but otherwise. So I'll tell you another great story. There's another genius professor at MIT who I didn't know was brilliant, and you're going to see why in a minute. But he came into class on the first day, and he used to talk like this. He'd say, "Hello, well, I won't give his name, but he says he'd come to the board and be like, "Oh, there are no erasers. I know there are erasers," and he'd reach down and pull one up, and then erase. That's the story. So I thought the guy was a buffoon, and later on in life, you read some of his papers and you realize the man is no buffoon. So people aren't always what they appear, right? I should have learned that long before college. And apparently he did that on almost every time he started the term, because a friend of mine told me the story before I took the class with him, and he did the exact same thing again. All right, that's it for today. Anybody with really long arms who doesn't care about getting chalk all over their clothes? Want to get some extra credit and dig out some erasers?